是你的组员要交给你，这个时候。对啊，我后面 PPT 我不给你。看这有没有什么字我不会读？哇，好多问题啊！
已解锁，请启充话筒。
I just decided to just I left my breakfast. 完了，终于完了。哎呦啊！那个
这两个符号讲念啊，我有忘记了，这个符号跟这个符号。
phi 跟 psi。
phi 跟 psi。
哎，对呀，I bring some snake, which you can take. Yeah. Nah. So please keep the place clean. Throw the rubbish away. Yeah, you can try to distribute. Eric, 拿去分一下。不要这样那个我不是你妈。
所以要破工资啊！
你妈付你有没有付你？
会有吗？不会啊。
啊，
会有，
应该不会吧？你要开始啊，我。
还没有送你懂的。
OK。Okay, we should start soon. Start in 5, 4, 3, 2, 1. Okay, so we have left the last group of the day. We leave the topic of McKay correspondence to the last of the day. Anyone have idea why is it the last one? Okay, one of the reason is assignment. There's a question on blow up. Very related, I think. Saya, are you going to calculate it later? Saya will do some calculation. Not sure it's the assignment question. We left it as a secret. Another thing is actually also this is the point where I left my research also. This is the last thing I have looked at before I graduate. Yeah. No, I mean I like before I graduate. Yeah. Okay, so this thing is pretty important for me also. Yeah, so we'll start with Ivan.
Hello, testing. Okay. Thank you, teacher. So I'm the first to talk about the financial group first. Okay, so we have 5 topics, which is the clarification of financial group, the financial group of 3, which is SO3, SO2, SL2C, and AD lacking diagram. So what is the clarification of the financial group? This is the special unity group SU2, the special alternate group SO3, and the special linear group SL2C. It's a classification result in group theory and like theory. So these groups are interconnected through covering maps and complexification, which leads to a unified classification scheme. So they have their relation. So cos to SU2 is a double cover of SO3, and SL2 is a combination of SU2, and SU2 is a maximal complex double of SL2. Later we will discuss about this one. So what discuss about for this one? The orbit simulator theory. This one actually we have learning in our class. So I simply to talk about, let S be the set on which a group G that acts, and let S be an element in S. So, and let GS and BS be the simulator and orbits of S respectively. The corresponding GS to is a bijection between OS and the set of less concept of GS in G for every element G in G. So we prove that. Want to show the corresponding GS is bijection. So this is clear that this correspond is suggestion because for all X is in X, and every GX is correspond to one GX. And let G and G prime be the element in G. So we assume that GGX and G prime GX, then they exist H1 and H2 in GX. So such that we know that G H1 and equals to G prime H2. So we said that G H2 and H1 -1 is equal to H. So we get G equals to G prime H. For some H is in GX. So we have G Hx equals to X since H is in GX also. So we know that GX is equal to G prime X. So we know that the corresponding is also injective. So why I'm talking about for this theorem? Because from this theorem, we can show that the finite subgroup of SO3, they have classified with five types. Here, now it's only got 2 letters, next got 3 more. So the finite subgroup of SO3 are the rotation symmetric group of a regular polyhedral polarized solid, and they are cyclic invariants. So what is they? They are the first one, cyclic group CN. This is the rotation around a single axis by 2 pi divided by n. So for example, the symmetry of a regular n-gon is in 3D space. And second one, this is binary dihedral group CN. This is a symmetric group of a regular n-gon, which is including the rotation and refraction in order to end. But in here, SO3, this is only the rotation only, but it is not refraction. But it's in others, they got that. Next one is the third one. This is the binary tetrahedral group. So the rotation symmetric group of a regular rotation is order 12. And the fourth one is binary octahedral group O. So the rotation symmetric group of a regular rotation is group is order of 48. And binary isohedral group I, the rotation symmetric of group of a regular eccentric or dodecahedron. This is order 60. Also, the group T, O, and I are the polyhedral group. For each G is in SO3 and D is a double cover G dot in SU2, where G dot is 2G. So what is double cover? Let's just discuss about. The double cover is equivalent Jack-School principal bundle, and this is an entire space with the local section with the 2 element space. A double covering group of a topology group such as the Lie group, a group extension of index 2 formed by a topological double cover. So a double cover may also used to refer to a non-topology group extension of index 2, for instance, extension of finite groups. And next, just now we got talk about SU2, the relation between SU2 and SO3 is SU2 is a double cover SO3. So for F is from U to R is actually is 2 to 1 mapping, which is in a statistic function. Since FU, so FU is equal to F negative U. So we know that all the things are. So SU and negative U are mapped to the same R. So we say that S2 is double covers SO3. Since the map U to R is a 2 to 1 and but is not 1 to 1. So SO3 and SU2 clearly cannot be the isomorphic groups. However, for significantly same neighborhood around the identity, that neighborhood will include the exactly one U or negative U where all U is in SU2. So locally, in the neighborhood of identity, they are isomorphic. There are hints of this in many others area of the usual discussion. Three-dimensional discussion around the representative SU2 and SU3. For example, SU2 has a three-dimensional representative. This exactly is correspond with SO3 also. So, but before that, we discussed about the theorem. This is Conway theorem in 1984. So what is the theorem talking about? They exist a 2 to 1 homomorphic mapping to the group SU2 onto the group SO3. So if A in SU2 maps onto RA is in SO3, then RA is equal to R negative A. And the mapping may be chosen so that RA is equals to like this, the form. So what is it? This is a parallel spin matrix for this. So let's now talk about the connection between SO3 and SU2. SU2 is the set of all 2 times 2 complex metric of the determinant equals to 1. So they define that A and A is equal to 1, where A is the alpha, beta, negative beta, alpha, where we know that the determinant between A alpha square plus B square is equal to 1. So they are the 3 independent polynomous fraction to simplify an element of here of SU2. So here is the 1. This one is A equals to the long arc, where we know that the theta is in 0 to pi and here is 0 to 4 pi and sun is in 0 to 2 pi. So this object that transport under the SU element like these are called spinor X alpha, where alpha is equal to 1 or 2. This has the analogy of vector is in the 3-dimensional rotation SO3. So S2 prime is equal to A alpha beta X beta. So where also is the same one, alpha and beta is equal to 1 and 2. So just now why we discussed about the theorem. So before this, just now the theorem talking about, we know that the representative of SO3 are also representative of SU2. So in addition, they are the spinor representative of SU2 that have no origins in SO3. That the defined representative of SU2 with 2 times 2 element of A alpha beta is the lowest dimension spin representative. Okay, let's introduce about the finite subgroup of SU2. The finite subgroup of SU2 were classified by Felix Chase in 1984. SU2 is just now we talk about SU2 is context a 2 times 2 unity metric with determinant 1. So this is also known as the Kleiner group or binary polynomial group. The quotient SU2 divided by plus and minus I is in SO3 means that the finite subgroup of SO3 leave the two double cover in SU2. They are given by the following list up to the conclusion, which is also the same with 5. This 5. It's also for the first one is cycling group CN. So this is generated by a diagonal metric of the form. So is order n, and where n is because n equals to 1. So this corresponds to rotation in SO3 by 2 pi negative 2 pi divided by n. And the second one is binary dihedral group Dn. So this is the double covers of the dihedral group Dn of order 4n. Just now is 2 and now it becomes the order of 4n. So they can be present by for AB, A A times 2n is equal to 1, and B squared is equal to A times A n times, and B negative 1 is equals to A negative 1 times. So for example, the quantum group SQ8 is also in D2. And the third one is binary tetrahedral group T. This is the double cover of tetrahedral group A4 of the order as 24. This and related to the symmetry of a regular tetrahedron. And the fourth one is binary octahedral group O. This is the same is double cover of the octahedral group S4. So it's become the order is 48. And this is related to the symmetry of a cube or octahedron. And the fifth one is this binary isohedral group I prime. This is also is the same one is the double cover of the isohedral group A5 with order of 120. And this is related to the symmetry of the heterogon and isohedron. So yeah. Oh, sorry. Okay. So this is finished for SO3. Just now we got talk about the SU2 is the maximum complex subgroup as SL2 and C. In the medication, the maximum complex subgroup K of a topological group G is a subgroup K. This is complex space in the successful topology and maximum among such subgroup. So, maximum complex subgroup play an important role in the classification of like groups and especially semi-simple like group. But the maximum complex subgroup of like group are not in general recruit, but this is unique up to congregated, so they are neutrally. And then the maximum complex subgroup is a maximum subgroup amongst complex subgroup. They are rather than being a maximum subgroup that happen to be complex. But in any case, in fact of maximal proper subgroup are not in general complex. So next, we talk about the final subgroup SL2. So since SL2 is the maximum complex subgroup SL2C, so any final subgroup SL2C is a concrete to a subgroup of SL2. This followed from the unitary traits, which is the any subgroup of SL2 represents some permitted inner products, and just you can to be conclusion in SL2. So consequently, the clarification of final subgroup as SL2 is essentially to that of SU2. The final subgroup SU2 are well known and correspond to the binary polyhedral group. This is the double cover of the classical rotation group of the regular polyhedral in our tree. Also, all the final subgroup SL2 are linear reducible. This means that it can be represented as unitary matrix. And also the final subgroup is become of SL2 is 5. Actually, this is usually is the same with SU2. Everyone can see again for this. This is all the things, the details same with SU2 together. Okay, this is a finish. Now we're talking about ADE Daikin diagram. So the ADE classification consists of 3 infinite families and 3 expression case. So the first one is AN. For all n is bigger or equals to 1. So this corresponds to the spatial linear light algebra. And the second one is the DN. For n is bigger and equals to 4. This is correspond to the even dimensional ocular light algebra. The third one is E, but this is only 3 types. Is E6, E7, E8. This is expressional light algebra. So this diagram are called simply light because it's just as simple. So you can see the downstairs is the diagram of this 5. So let's introduce about the equation of AD diagram. So at here, it is the table inside. You can see for all type, for example, AN is cycling, and then it is n z divided by n plus 1 z. This is the group. And then at the side got the polynomial equation. This is from SU2, SL2, and also still got one more column in here, SL3. Because this is the tablet two biggest, so it already, so it cannot show in here. So I write here as SO3. And also still a remark here. For E7, the group is in S4, no in A4. This is wrongly, so I added it here. So everyone can see, but never mind, we will prove for that. How to show the equation, because later we will use for that. So for n, the group G is equals to Z divided by n plus 1 Z on X on C square where. So for X, Y is in zeta X and zeta negative 1 times of Y, where zeta is equals to E2 pi I divided by n plus 1. This is a primitive on x plus 1 roof of unity. So we seek the polynomial of f x y z that are invariant under G. So f of zeta x and zeta times the negative 1 times of y is equal to f x y. So since zeta xn is equal to n, s power is equal to s plus 1, so we let u equals to u equals to xn plus 1, and zeta negative 1 times of y is also let it become to y equal to v. So v is equal to y n plus 1 times. And then for times between them, I will also get w is equal to xy. This is the setting one we set for that. So what is the relation between them? We can know that uv is equals to w n plus 1 times. So the invariant rings in C xyg is equals to CUVW times divided by UV minus WM plus 1. So the quotient singularidity for here is described by the equation UV equals to WN plus 1. So we times that just now x equals to u and y to be v and z to be x, then we can xy is equals to z power of n plus 1. This shows that the equation of finite the subgroup of SU2 just now we show that. And also from above, we plug in and since this is the projective space, so we can plug in and minus to become plus, and show this all things so become the finite subgroup of SL2. And also, and before just now we get that UV equals to WM plus 1 times. Then we sub that U equals to RE I zeta times, and UV equals V equals to SE negative 1 times, and W is also is the same one as UV. So we can get all the calculation to become x squared plus y squared equals to n z n plus 1. But since it's a project space, so it also can be written x squared plus y squared plus z n plus 1 equals 0. And here, this is the equation of finite subgroup SO3. And continue with the Dn. The Dn singularities correspond is to the hedral group of D2 n plus s minus 2, which is the symmetric group of a regular n minus 2 God. We divided its equation through the invariant theory. The group D2 n minus 2x on C with generator, which is rotation rho is x, y is equals to zeta x and zeta negative 1 times of y, where the zeta is equals to E2 pi I divided by n plus 2, n minus 2. This is the difference with just now an. So, and also they have the refraction, which is the tau. The tau is xy is equals to yx. This is the fraction. So we're doing the same thing with just now with an together. For all the things, we will get all the details and here. So that we just now we set u, v, and w, and then we discuss for all the calculation. We can get it here is the x squared minus x y plus x n minus 2 at there at the center. So this show that the equation of finite group SU2 And also since it's projective space, so it also can be right at this one. So the minus become the plus. So this is, and we write for that. This is a financial group of SO3 here. And also we plug in as F1, F2, and F3. So it's become the SL2. And then continue with is. Yes. Okay. It should be F1 to the N minus 2. Okay. Okay. Later I check for that. Later I check for that. I think maybe you got writing or something. Your time is up. Never mind, I still got 3 more and easy to talk. For E6 is doing, yeah, what we need is only is easy one. So doing the E6 for the same one. So for all the details that you guys want to see can see lah. And then you also can get the x times 4 and plus y3 and z square equals 0. This is the equation of sine group SO3 and SO2. It's also similar for just now. We time F1, F2, and F3 equals to x, y, and z. So this become the financial group of SL2. And for E7, it's also the same thing, the equation for all the things. If you want, you can come and take from me. And then prove that all the things it become x cubed y plus y cubed plus z squared equals to 0. This is the financial group of SO3, and also similarly the equation to SU2 and SL2. And then the last one is E8. This is all the proving. That also the same one. If you want, can take. And then until the behind show that x times of 5 and plus y cubed plus z squared equals to 0. This show that the financial group of SO3 and similarly to financial group of SO2 and SL2. Also, this show the okay. Okay, this is the and now so the equation later I'm proving it here. Later my roommate will use this to do for the blow up. Thank you. So, my teammate Syed will do for the blow up with using this equation. If you want, you can take a photo for this first. Okay, like this one. Thank you. Any question here? Okay. The thing is, why your double cover definition is like so low? So there's a lot of them, and then which one are you using? Actually, they still got many, but I only choose the part the duration only. This is like, you know what's the it's house space. No. Right. So why are you writing? Are you using it? It don't come from where on the definition. Online the online one, the book one. That one one 一个网站他给了the website he give one. And then actually he write for many paragraphs. The first paragraph is this one, and then he said that this is separate with different type, and then the downstairs for the topologies, the group is one type of steps. So I put it inside. So I mean that one is not live group, the group doesn't sound live. Okay. Later I change for it. Okay. Oh, league group only, yeah. Okay. Oh, like. Sorry for that.
This one. So are you sure that one is correct? However, for a sufficiently small dynamical identity, the neighborhood actually objective one. This is a double cover.
It is from West side also.
Where's
From
the cheat?
others, the theorem they talking about for this one. This one they talk about is it? Yeah, let me think. Yeah, this one is the explanation for that. They is talking about the topic is SO2 is a cover SO3.
Could be tangent space there, but it can't be the inverse of the 2 to 1. Doesn't make sense. I don't think it makes sense.
Okay,
I don't think so.
maybe later I try to find more information. I try to find more information.
Under what?
Hmm?
Under what? Doesn't make sense also, if you just look at SU, what you mean by U or minus you just view it because you are able to around there. So I think you are talking about inverse of some man. Yeah, I think this line doesn't make sense. Okay, next. Okay, other than the thing before, actually I like the part where you come up with the invariant function. I think you should write those parts better. I mean, like write it in detail. I mean, the part about when you figure out the invariant polynomial. After this, I want you to focus by the right of these things.
The proof the is proving. Oh, okay.
Yeah.
Yeah, sure, no problem.
I think you focus on right. I think this far is good.
Oh, basically, groups, especially the spin volume matrices, which is applied in quantum mechanics and possibly in string theory. And I would like to know whether finite subgroups can be applied on quantum computing.
On quantum computing, I know quantum mechanics can be used. It can be used for that, but quantum computer. This one I don't sure. Maybe if I find more information, I can tell you.不懂在讲什么，讲完。I don't understand. You're talking about. Can you talk more clearly or what? Because my English is very bad lah. Very slowly or.
Okay. Can you give a sense of how Klein went about classifying the finite subgroups of SU?
The clarification of financial group SU2. Yeah.
What's the general idea of
Yeah, slowly. Sorry, yeah, talking slowly.
what was his proof basically?
Oh, how you become like this one? Is that I'm using the double cover from SO3, so from SO3 translate to SO2. Certain, what is certain already?
That he showed that there are finite subgroups SO3 and those come from regular polyhedra.
Yes.
It lists those two finite subgroups SU2. So how do you know that's it? How do you know there are no other finite subgroups?
Maybe I need to find more information.
He actually playing playing in another called printing model. And then he obtained invariant formula of SL to solve this. And then he ends up classifying formula that has a similarity and but how it exhausts all possibility of finite number of SOI. Thank you.
Okay. Okay. Others got question? No. Okay. Here one. Next, I pass to my teammate Adrian.
Sudah. Cannot use my. Can you also not use my? 可以用讲话吗？啊，susah. 嗯，啊，什么？不要了。I'm the second person who's gonna present, which is uh previous part Ivan is only classifying all the finite subgroups, which is the classical McKay correspondence where you can do corresponding McKay quiver to the to the finite subgroup that is classified by Ivan. But I'm not going to talk about all those. What I'm going to talk about is a crash course for group representations, mostly group representations, because there's a language that you need to use for you to construct a McKay quiver. And then at the end, I will define how we would want to define construct a McKay quiver. Then actually drawing an example of McKay quiver, that one requires character theory, which I'm not going to talk about. So Joel, which is next to me, which is after I present, so he's gonna do that. And so let's have some actually motivation. But the motivation I talk already lah. Forgot to skip a line here. So Kleinian singularities are. Kleinian singularities are is the singularities whenever you take the finite subgroup in SL2 then when you act linearly on C2, then on the quotient space, you can see that you have a singularity at the origin on each cases. Okay. This will be particularly discussed by Lydia later. And also later on, our lovely Said will do blow up on all these origins and to recover again the ADE thinking diagram. And then the second McKay correspondence, which is talk a little bit about this lah. So whenever you take a finance group from SU2, and then when you construct your McKay paper, if you guys haven't known lah, okay, later you know, and then you see that each of the McKay paper will have a affine simply laced thinking diagram. What is an affine simply laced thinking diagram? It's just the diagram that looks like this. So just now Ivan's one, it's just a simply laced thinking diagram, which it take away all the trivial representations. So you can see that for the class A, Ivan's one will be a line only. So the trivial representation will be excluded. But in a affine case, the trivial representations will still be there. Okay. So this is something that we felt weird about. Okay, whenever we go from a representation theory approaching the McKay correspondence, the trivial representation will always be there. But if we do blow up on singularities like Said, then you cannot recover that thing. So you get a simply laced thinking diagram only. So it's not the affine case. So there's something to talk about in the future, maybe. Okay, so I'm going to start my crash course on on group representations. So what is group representations? Given a group, and a grammar field K. We denote this as yeah. And then the representation of G over K is a homomorphism that sends the element of G to a linear map. And the linear map is acting on a vector space V, which you can set yourself. And then obviously the dimensions of the representations will be the dimensions of the vector space that you take. Okay. So there's a lot of definition for representation of G over K. Some people use homomorphism. Some people say that it's a group action. Some people even use matrix representation. But for anyone who took linear algebra before, we know that every linear transformation is a matrix transformation. So it is very obvious that you can write it in the matrix representations. So we are not just using this language of homomorphism, because this language later on will be used by Joel, my roommate. Okay, my roommate. So actually, a representation you can see it as a G module. How to see it as a G module? It's somewhat like a group action, you know. But this group action, you take it as a scalar multiplication for your module. So that's all. And then you can prove it. This is very easy to prove. Exercise, right? Exercise. So you can define your scalar multiplication GB to be something, and then you can verify that it satisfies all of these conditions that it is in module. Okay. Very straightforward, very easy. Oh, I forgot to tell you guys something. My slides number is not real. Okay. Because I don't use begin frame for every frame. So the slide number is not real. So if you want to ask something or you want to remember the slide, you remember the name. Don't remember the page. Yeah, you see, still 5/30. Scam. Okay. So when you have a representation in group theory, you guys know I have a group that I want to know what's the subgroup that I can have. And naturally, if you have a representation, you want to know what kind of sub-representation you know. But you cannot just take sub-representation, whatever that you want to take. So there's actually a special subspace of V that you consider that you can take it as the sub-representation. So we call this kind of space a G invariant or G stable subspace if okay, let me write it out. My eyes are not good. So if what if rho of G W W for all W in W and then for OG G in G. What does this mean? This means whenever you take an element in W, then the corresponding linear map should also map W into W. So you cannot take a subspace and then the corresponding row representation that you consider it maps the something inside your W subspace, vector subspace, to something outside of your vector subspace. Okay. So obviously, if you want to have a sub-representation, you can just always restrict your group homomorphism row to W. Okay. So you only can do this whenever your space is G invariant. Does that make sense? Agree? Agree? Okay. So a very easy example, the trivial representation. So it will sense all the elements in G to an identity linear map. So if you think about it, then any subspace that you consider in your V is G invariant. Right. So identity function will map something into itself. It stays wherever that it has to stay. Okay. So whatever subspace that you take, then it's still a subrepresentation. G invariant. Okay. So there's another kind of representation. It's called the regular representation. This sort of representation is a little bit weird. Because the vector space that it takes on is different. So let us now define the vector space that we are going to actually consider our regular representations. And this sort of, and we denote this as Kx, and normally some people call it group algebra, some people call it group ring, some people call it the K vector space. It can be anything. So this is how you define it. You take the linear combinations of K K scalar multiplication, and then you take your finite set as the basis for this vector space. Okay. Then the rest is just obvious. So you can define addition and multiplication like normal like normal, and then you can verify that this dude has a ring structure, algebra structure, and also it's a vector space. Okay, so this is the regular representation that I'm talking about. Just now, the B that we are taking is whatever B that. So whenever we take KG as the vector space that we are taking, then we are saying that we are doing regular representations. So in this case, I'm multiplying the scalar from the left hand side. So it will be the left regular representation. Okay. Agree. Okay. So normally, yeah. So now a representation. We have a representation. No mathematician likes to make things easier. likes to make things nice, likes to make things simple. Okay. So what is a simple representation? Okay. And you can see that it's simple as if it cannot be reduced or it cannot be decomposed. So just as I said, if there is a G invariant subspace that appears in your vector space V, then obviously it will invoke a subsection of your representation. So this definition is straightforward lah. So if a representation is simple or you call it irreducible, if and only if you have no proper G invariant subspace. I can say that it can also be seen as a G module. So you can also say that it contains no proper submodule if we are looking at it as a G module definition. Make sense? So direct sum of representation. A little bit boring, but a lot of definition. But this is the language that we need to use. No choice. So direct sum simply can say that it's just two tuple. And then the direct sum here is a vector space direct sum. Now I call it external because it's like you take two representations and then you direct sum it together. It gives you something. And you can actually prove that the direct sum of two representations is also a representation. But I'm not proving it here. And you can as you can see in matrix notation, this obvious to you. Obvious, huh? Very obvious. So there's another one that we call the internal direct sum. It's like you have a representation. If this representation is the direct sum of two representations, two sub-representations, then you call it an internal direct sum. Okay. So in linear algebra, the two internal direct sum of the internal direct sum of the vector space define like their intersection has to contain element 0. Okay. And then again, mathematicians like to make something simple and then also make something not that simple. So if you make it too simple, then we have nothing to talk about at all. So a representation is said to be semi-simple, middle simple. Okay. Or you can say that it's completely reducible if and only if you can write it as the direct sum of irreducible representation. That makes sense. Can you guys see that this is finite whenever your representation? No. I mean, if your representation has a finite dimension, it's finite, the dimension is finite, then you cannot really decompose it into like infinite chain. Can you do that?
The point here is you split it into direct sum. Right?
Yeah.
You could have irreducible, but you cannot split it. So it's not semi-simple in that case. But I still have an irreducible. Okay. So indecomposable.
Indecomposable? No. Right. So our main goal I didn't know our main goal. Our main goal in this group representation session is that we want to go for shit theorem. Do you guys know how to pronounce it? McKay theorem. Very fancy thing. So to prove this, okay, from now on, the thing that we, oh damn, the things that we do, okay, let me be fast, Okay, the things that we do, is actually laying the foundation for the okay. So, a projection. So so we find a map, it's called a projection. It sends everything in the subspace to the subspace, okay. And then we say that a map is equivariant whenever it is unaffected by the G action. Okay. So do you get what I mean? So if you act on it, or you map first, or act on it, and map is the same thing. Okay. Now this lemma is the key line at the finishing blow to the key term. So I will not talk about the proof. Very easy one, this thing. So if you have a V, then you have a W. W is a, let's say this is W. Okay. So what does pi do on this thing? So pi will sense everything in W. W, right? Everything to W. Then since in a vector space, the direct sum must contain a zero here. So the rest of the not included in W space will be sent to a point which is zero. So using this property, we can see that the kernel of this pi map is our desired G invariant subspace that gives us the direct sum. Okay, this is the idea. So the proof it yourself. Then the McKay theorem. Okay, the important thing is that you consider a projection, right? On V to W is a sum representation. This is not necessarily equivariant. So to prove this thing, we need to make another new linear map such that it is equivariant. So this is what we call the averaging trigger. Okay. So and to mention why the factor of K cannot divide the order of G, because Justin told me if the character of K divides G, then you will be dividing by 0. So this map will not make sense. Okay. So then to prove this, you need to show that it is equivariant, you show that this is a projection, and then by the previous lemma, this will give you your G invariant subspace that will decompose your computation into U times W. Okay. Cepatnya. So okay, fine. Thank you. So the corollary is simple lah. If I can decompose into two things, then I can decompose into R things lah. So you can do your reduction on the dimension of V. Then same assumption. So you can totally decompose your V. Then your V is semi-simple because you write it in the chain of directional or reducible representations. Okay. So the tensor, I think tensor, just to mention, so it's not really that important. And yeah, the home space of a vector space is just a set of all linear maps. This is just a language that is used in the McKay quiver. So I'm gonna jump quiver because it's not important. Okay, McKay quiver. Okay, McKay quiver. What is McKay quiver? How to construct McKay quiver? To construct McKay quiver, first you need to have a finite group, and then you need the algebraic closed field. The order has to be in the multiplicative group K. Okay. Then we consider the left regular representation. Actually, you can consider every representation of G. And then you take the set of all irreducible representations of G. Then how do you construct this? This is you take the vertices as all the irreducible representations of G. And then to know how to draw it, you need to know how many edges here to here, there to there. So this is how you This is how you find your edges. Okay. So if you take, okay, to explain this intuitively, you take di to tensor with the fixed representation that you fix, and then you count how many decomposition, how many vj is contained is in this representation, and then that is your number of arrows from here. Okay, very easy. But this formula, I unique character theory to calculate this to be for it to be easy, because you cannot just brutally compute all linear maps. You know? Okay. So that's all. Thank you. Thank you. Happy. Understand? Agree? 来 Justin 你要问我 OK. Is yeah, okay. The order of G lies in K excluding 0, so it cannot be 0. Of course, it cannot be 0. If it lies in K excluding 0, then can the character of K divides the order of G? Yes. Yes. So if it's in there, then it's impossible. Right? Make sense?
So take K to be R.
It'll be R. 2.2.
Yeah.
What do you mean by R?
And so okay, take that's number algebraic.
Mm-hmm.
What does it mean by order to be basically?
That actually makes sense. I agree. So let's forget about the assumption. so the main point that I do this is to not let the character of K divide the group, the order of G. Okay. Any sense? No sense? Yes sense. Good sense. Yeah.
With the direct graph.
With the vector graph.
I think like you skip the definition.
Tell me when you want me to stop. Mean this one?
So is that what you put it? Just a direct diagram.
Oh, Quiver is very interesting. I like it. So it's just a vector graph, yes. Hey, but it's fun. Okay, there's something called a Quiver representation. That you can plot all the edges, then you assign it with different vectors. How does it look like? If you're interested, you can look at Gabriel's theorem. It classifies all the quiver finite representation for quiver. Yes.
What is the affine diagrams?
Oh, in front. Okay.
Numbers here is the dimensional representation of you.
Numbers?
Yes. What do they mean?
What you mean? In this one?
So the numbers in the notes.
Numbers on the
1,
notes.
2, 2, 4, 3, 6, 5.
No. Have I ever thought about that? Let me think. Say it. What's your idea? The number represents. Because I never like really go and construct the material, because we need character theory for it. He's doing it. Okay. So I also wonder what does all these numbers mean? But I know this number 1, number 3, trivial representation. This one trivial. This one trivial. This one trivial. That one the root of trivial. So I don't really know what does the number of the vertices mean. Okay.
The numbers that correspond to the entity of the or component.
That one need here right. Question.
Back to the like
This one. Yeah, cat.
there an intuitive way to tell what the multiplicity in this representation?
Did I tell you? Are you listening to my class? So okay. Okay, let me. So this one is not written down, not really nice. Let me write down. Let me see whether I remember it or not. Okay. Vi tensor with this dude. What's this dude? So R. And then this is actually equal to direct sum. So J. Right. So I think looking at this will be nicer. So it's like you are trying to decompose this, which is why the McKay theory is very important, because it guarantees that this thing can be decomposed. You can show that this is semi-simple. Okay. And then this counts at how many Vij contains in the decomposition of this tensor. Okay. How many copies of Vj is in this decompositions?
That's where you use the McKay theorem.
The McKay theorem is to actually guarantee that we can write it like this. No, if not, then it will be funny. It's important. It's very important. That's why for you want to construct a McKay fever, you have a lot of assumptions. Those assumptions is for the theorem. For you to decompose it. Great. Happy? Risha, happy? Risha? Ina, happy? Okay. Agree or not? Chưa? Agree à? Tán đi nha ơi! Bạn à? Cái thảo玩嘛？哎。Okay. Something funny is this. So, McKay correspondence you can go into with representation way, or you can have it from door.
Resolution well.
You know, and you know. Okay, next. Who's next? Who's next? Favorite muscle Joel. Whoever don't agree with him, he'll bench you and then he'll throw you to the ground.
Okay, thank you, Adrian. My name is Joel, and I'm going to talk about the McKay quivers for the finite subgroups of SU2. And this is the outline of my presentation. So my first groupmate, Ivan, has already classified all the finite subgroup of SU2. So what is left now to see the McKay correspondence, which I will talk shortly, but Adrian has already talked about it just now. So what is left is to construct the McKay quiver of the finite subgroup of SU2. And this is where we will recover the affine AD linking diagrams. And then, like Adrian said, the dimensionality of the home space is not really that easy to compute by brute force. So which is why we need to employ character theory. So in character theory, I'll just talk about the basic properties of character and then talk about inner products. And then finally is what my main goal for the talk today. Okay, so in 1979, John McKay observed that there exists a one-to-one correspondence between the non-trivial finite subgroups of SU2 and the simply laced affine linking diagram. So simply laced just means between two nodes, there exists at most only one edges between them. So, which is the case of AN, DN, E6, E7, and E8. Is why it's called ADA type. Then, yeah, this observation is known as the McKay correspondence, and we'll construct this the diagrams through character theory. So, throughout this presentation, all groups are assumed to be finite, and vector spaces are assumed to be finite dimensional over the field C. And like what has been explained just now, from representation, it's easy to go into easily translate into the language of G modules, and this is something what I will do throughout this presentation. And for a representation for any G, it's mapped to a linear transformation from V to V itself. So we know that any linear transformation, there's a matrix representing it. So it makes sense to talk about the trace of a representation. So the character of a representation denoted by chi is simply the function given by the following. So we map an element of G, and then we just map it to the trace of the representation of G. So there can be multiple representation on a single group. So it's not exactly clear that it's well defined. So in order to show that it's well defined, we suppose that these two representations corresponds to V, and then we can have this relation for some fixed T. So you can just imagine this as being a change of basis. So when we go through the trace of it, we see that it remains the same because trace is invariant under conjugation. So this is how we show that character is indeed well defined. And then the simple result that it's a basic properties on the character says that the character on the identity is simply just the dimension. And then for any K conjugacy class of G, for any elements from the same conjugacy class, the characters must be the same. And then I denote here, this one represents the character for the tensor product. And so basically, this tells us that the character of tensor product is just equals to the multiplication of the characters. So you can see that it's easily verified. For example, for number one, let's say dimension v is equals to n. So the characters of, the representation of E is simply associated with the matrix, the identity matrix. So it's an n times n identity matrix. You take the trace, it's just equal to n, which is the dimension of V. Okay, let K be a conjugacy class in a finite group and chi a character of the representation of the group. We define chi of K to be a common value given that chi takes on all elements of the conjugacy class K. Because from the previous proposition, any element from the same conjugacy class must have the same character. So it makes sense to define this, which also shows that it is actually well defined. So why do we need this? Is because we have something called a character table. And so for the columns, we'll find whichever conjugacy class that you want. And then to the column, we match it with the character that we want. And then you give out just the value for the character on the conjugacy class. So there's a convention that we will use here, is that the first row correspond to the character of the trivial representation, and then the first column correspond to the conjugacy class containing the identity element, which is just E. Okay, then now we can talk about the inner products of character. So what it is defined as, okay, let G to be a group and phi and psi to be two characters G to C. So you take the inner product. The inner product is simply just given by this formula, where the bar represents the complex conjugate. So one can actually verify that this is indeed an inner product. And then we have the grand orthogonality theorem, which I won't prove. It's just, okay, if these are two characters of two irreducible representation of a group corresponding to the modules V and W, then their inner product is equals to the Kronecker delta. So, which basically just says that the characters of the irreducible representation of a group are orthonormal with respect to the inner product. So, Adrian has talked about the HT theorem just now, because we consider the ground field to be C. So this is always satisfied. So for any V here, we can decompose it into a direct sum with each of the VI to be irreducible G submodule of V. And then these MI are simply the multiplicity. And I don't know which convention that we use, because some authors have their MI written in the front and some have it written as a power. So I'll just use this convention because I'm not really that familiar with the field. So yeah, I'll adopt this convention. No, this one just denotes the multiplicities. So it's actually just the same as M.
But usually at the top is tensor product. If like number square.
Yeah, because there are some that uses MI in the front, some uses MI at the top. Not really sure which one is the convention. I just follow which one is my main reference. So in that convention, the powers don't really represent the power. It's just the multiplicity of it. So as a corollary of the grand orthogonality theorem, which says that the characters are orthonormal with respect to the inner product. So we decompose V into its irreducible component with multiplicities, and what we find that if we take the inner product of chi, which is the character for representation, corresponds to the module V, and then we take the inner product with its component, we'll just get the multiplicity of that corresponds to the irreducible component. So the proof is actually quite easy to show. You use the fact that the trace of a direct sum is simply the sum of traces. And so chi, which is the trace of the V here, but V is equals to this direct sum. So it's equals to this one over here. And then by the property of inner product, we can just pull out the sum mi. So by the grand orthogonality theorem, the inner product reduces to this one, which is because we sum over the index I, so it's only one when the index I is equals to j. So which leaves us with mj, which is the multiplicity associated with vj. This is an quite useful proposition. It tells us that if G has a group and we consider the group algebra, and suppose that it decomposed into the sum of its irreducible component, then the number of irreducible components is exactly the number of conjugacy classes of G. This proposition is useful for constructing the to know how many irreducible representation we can have on the finite subgroup of SU2. So we finally arrived at our main goal today is to construct finite subgroups of SU2. But I'm only going to talk about for the cyclic subgroup of order n because it's very long. So I'm only considering one, but the rest, the ideas will remain the same. But first, we need some, because to construct the McKay quiver, we need dimensionality of the home space, but we haven't really talked about the dimension of home space, so which is what I'm going to treat now. So for G module homomorphism, its kernel and its image are G submodules of V and W respectively. This is easily shown because G module homomorphisms are linear. And from the theory of vector spaces, kernel F and the image are the subspace. Then we by what this we define just now, a submodule or G invariant in Adrian's language, we simply just need to show the closure under the group action, which is not that hard to see because if you consider V in kernel and then G in the group, then you take the F of GV, you take out the G, then F of V is just 0. Then indeed GV is in the kernel of F. So this is Skur's lemma, it says that if F is a G homomorphism between two irreducible G modules, then either F is a G isomorphism or F is a zero map. So by the previous proposition, the kernel and the image are submodules, but since V and W here are assumed to be irreducible, so the only submodules that are in V and W are either zero or the whole space. So since it's irreducible, either kernel is equal to zero or kernel F is equal to the whole space, and either image is equal to zero and or image is equal to the whole space. So you can argue what happens when kernel of V or image of F is equal to zero, then it's just simply the zero map, right? Because if kernel V F equals to the whole space, then F takes on any value becomes zero. So it's simply the zero map. So if kernel F is equal to zero and image of F is equals to V, kernel F equals zero implies that it's an injective. Image of F equals to the whole W, not V here. It just simply means that it's surjective. So in that case, F is an isomorphism. So the Screw's lemma is actually used to prove this result on the dimensionality, which we will use later, which just says that if V is decomposed into its irreducible component, then the dimensionality of the home space is simply just the inner product between the associated characters. So the first line is by assumption because V is equals to the direct sum. And then this part is purely an algebraic result, if I'm not mistaken, because I think you can pull out the direct sum if it's in the first component, and you can pull out direct product if it's in the second component. So direct sum in the first component, you can pull out. This is, I think it's an algebraic result. And so by Screw's lemma, the home, because any morphisms between, any homomorphism between Vj and Vi is either a zero map or an isomorphism. So it's either a dimension 0 or dimension 1. So this reduces to its dimension to be Mi, because recall that the Mi are the multiplicity. Okay, this one. So maybe I'll just skip a lot of the computation here, but so basically Cn, which we denote the cyclic group of order n, from elementary group theory, we know that Cn is abelian, and so it has n conjugacy classes, and by the result that we have, the conjugacy classes are equals to the irreducible representations. And so if we define this one, representation, we let A to be a generator. So any representation can be characterized by what it does to the generator. So we define this one to be zeta power to k, where zeta is just n root of unity. Then for different values of k, we will get different value of zeta k. So maybe I've convinced that they're all different representation. So I construct here the character table for the irreducible representation of Cn, where the representation n, where representation sub n is actually just the trivial representation. So we get the character table. What we do is just we do substitution. Before that, we have to define the natural representation, but not enough time. So maybe you just take for granted that the natural representation is given by this one. So what we want to do is, so we have already computed that we have n irreducible representations, and now we just leave with to compute the number of edges between them. So this is just substitution by using a lot of results that we have done, and then I'll skip all this because these are all just substitution. Okay. So what we found that is actually when between the nodes P and Q. So if P minus Q plus 1 is not congruent to 0 mod of n, and P minus Q minus 1 is not congruent to 0 mod of n, then the edges are just 0. So between 2 points that are not adjacent to each other, basically this is what this is saying is that between two nodes that are not adjacent to each other, their edges between them is just 0. There's no edges between them. And for this part, because for the case where P is equals to Q minus 1 mod of n, or P is equals to Q plus 1 mod of n, is basically those nodes that are adjacent to each other. So those nodes that are adjacent to each other will have computed here to be 1. So there's one edge between nodes that are adjacent to each other and no edges between nodes that are not adjacent to each other. So this is what we are left, and then this is the what we call the affine linking diagram associated with the cyclic subgroup of order n. So the idea is still the same. To compute everything, we find out what's the irreducible representation for the finite subgroup, and then we compute the number of edges between them using character theory. And then I summarize here that these are all the affine linking diagram associated with the subgroup of SU2. And yeah, so up until now, we only talk about representation theory. So for the last two of my group members, they'll finally mention something about algebraic geometry, in which you see that from algebraic geometry, we can again recover these type of diagrams. So that's all from me. Thank you very much.
It's a bunch of one here. One of from coming from the. So just now it says that the character of E then is the dimension of representation. So I can represent the different dimension of representation. So that's why there's a lot of one at the Adrian line. So I mean, actually I'm curious about your structure. So Adrian report will just consist of one percent.
Yeah.
But I don't think I wanted to see see representation theory. Maybe you could, so in your report, only calculate for cyclic algorithm.
The cyclic group and the dihydral. Yes.
One of the other.
Wait.
Do those this all the representation. Huh? You already do A and B, right? So can you do one of the E?
But I think E5 is not that easy because even in the paper they use something called Dixon reduced character algorithm. So what they do is they find that algorithm and then they plug it into Python to do the thing. Yeah. So
You mean all the E there?
Huh?
For all the E.
Yes, for E5, E6, E7.
Adrian.
Huh? Oh. First one. This one.
For E6, E6 is
E6, E7, E8 all uses the Python thing.
all of them.
Yeah. When?
Why? I mean, like, here. What do you mean I'm using Python? McKay cannot use Python, right?
I mean for the construction of the thing, they use I think it progressively become harder and algorithmically. So
I mean, like, where do you have? So how they work?
true. Because right now we're just talking about how to construct it. But I think what McKay did is they approach it using the Y approach. So that's why they saw this observation.
Fine. I don't know what you say. Oh, no, but so have you found what's the representation they use?
The representation for E6.
Yeah.
No, I haven't looked into that. I just look at the cyclic subgroup.
Then how do you compare about the Python method?
In the reference that I use, that's what they did.
I mean, if they mention about Python, they should tell you what the representation.
Oh, to get that, I haven't really go into that yet.
Yeah. Like, what is it for a cyclic subgroup? Like E6. I mean, either one or E6 is the again. Huh? Yeah, I want you cannot put that.
And then how bad?
But I guess, I mean, if you, okay, I mean, to do your calculation just now, right? Basically, what you need is just character theory. You don't need the whole representation theory also. If you just need it, you just cite it, is enough. Like, no need to prove what McKay correspondence, the match key theorem stuff. Yeah, I think those proof are just like a more true proof.
Yeah.
I think like think it would be nicer to see like how these things get constructed. I mean, you treat representation theory as a tools now. It's not like I want to like know how it really feels now, but right?
Yeah.
I just want to use it.
So you want me to remove the representation part? Yeah.
I think you still have some calculation here, right? But I think Adrian one mostly is on. Yeah. Actually, I don't want you to go deep into representation theory. You just use it. Yeah. Can you calculate the cases here? One case, at least one. Yeah. Okay.
Okay, thank you.
How do you do full screen of this? 对不起，我没有睡觉，我很多现在我看不到东西。哪个这个？啊，OK，thank you，thank you。Alright，啊，Hello everybody. I believe you're all very tired, so I'm tired too. 我很累。Okay, anyway, I'm Lydia, and I'm going to be showing you how we obtain Kleinian singularities. Okay, be very brief. First, I'll set up, give you some definition, some proposition about the things, the terminology that we'll use. Then we'll talk about Kleinian singularities, and then I have a nice theorem at the end. Okay, that's all. So first, let's go into the definition of a categorical quotient. Okay. So let G be an algebraic group acting on a variety V. So algebraic group basically just means a variety equipped with a group structure. Okay. So a categorical quotient of V by G is a pair Y. Brain damage. What's this called? Help. Oh, phi, where Y is a variety and phi is a morphism from taking V to Y, such that phi is a constant on the orbit of the actions. And number two, for any variety Y prime and a morphism phi prime that goes from V to Y prime, which is also constant on orbits, there is a unique morphism psi from Y to Y prime such that when you compose psi and phi, you get phi prime. What does this mean? The first one just means that phi takes things that live in the same orbit and sends them to the same image. So it's like constant, like our constant function, right? We send everything to one thing. And this one is like constant orbits. Yeah. And the second one, I think if I draw a picture, it'll be pretty straightforward. So goodness me. Right. So we go to Y prime, and then there's a Y down here. So we have from here we have phi, from here we have what prime. And the definition basically just tells us that there exists psi that takes us from here to here. That's all. Next one, a categorical quotient of V by G is called an orbit space if V inverse Y consists of a single orbit for all Y in Y. The orbit space is denoted by V quotient G. Okay, what does this mean? Basically, if we take anything in Y, we send it back to the same orbit. What does this tell us about V? Actually, it's implied that it is actually bijective on the orbit space. That is, if you have any, say, x1, x2 in V, and then you find that actually phi x1 equals phi x2, then you could be sure that, they are equivalent in the way that they live in the same orbit. And then surjectivity is obvious because we require for all Y and Y. Right. The next one, spectrum of a ring is a set of prime ideals. This one, been said a lot of times. So, actually, this is an extra information lah, but spec R is actually a topological space equipped with Zariski topology. And then, in this space, we consider the prime ideal of the rings as points lah. Okay, now we have a G invariant polynomial. In this talk, we would consider more on complex C. Yeah, so we let K be C. Polynomials F in C, Z1, Zn is called a G invariant polynomial if for any element G in G, we have G dot F equals F. This means that the polynomials, this polynomial, right, no matter what action we take on it, it still remains the same. So like kind of no matter how you approach your crush, you still be our lead. Very sad. And the set of G invariant polynomials actually form a ring. Yeah. We call this ring the G invariant ring, denoted as C from Z1 to Zn superscript G. Actually, it's my personal interpretation of it lah. You could say, how is it different from normal C, Z1, Zn? Good question. But we need to consider that this C, Z1 to Zn has already a group action on it. So you could think of it has some points that kind of stick together because they have their own orbits in some way. That makes sense. Right. Next, we have a proposition. Wow. Okay. Let G be a finite group of order n acting on an affine variety V. Assume that the characteristics of K does not divide n. Now we said X to be defined as a spectrum of KV superscript G. Then X is an orbit space for the action of G on V. What does this tell us? Actually, I just think that it's a pretty neat proposition because when we think of the spec, right, we are looking at prime ideals. So basically, we're taking like a group action, right? And then we correspond it to a prime ideal, which corresponds with an affine variety, a set of affine varieties in the AG class. Yeah. As for Y characteristic of K does not divide n, this one, yeah, Adrian did discuss about it. Basically, I would say that this makes it so that everything is quote unquote nice. Yeah. And the proof you could find in Igor's textbook. Yeah. Okay, next. Oh no, I accidentally gave you guys a spoiler. Now we're gonna talk about Kleinian singularities. Question: Do you think that C power 2 quotient by G is an affine variety? Dun, 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 dun. Yes, no, yes. Do you think? Yes, no? Oh, good question. It's an irreducible algebraic set. Algebraic set is like a set of points which if you put it into the polynomial, it goes to 0. That good for you? Okay. You think yes or no? Yes or no? Half? Okay. I think yes. So why? Let's look at some propositions that will support my claim. Okay, first, a finite generated group G subgroup of GLN CX on C Z1 to Zn. Then G and then C Z1 to Zn superscript G is finitely generated. Do you buy? You buy it. Actually, if you have a finite amount of quote unquote finite amount of stuff and then finite amount of actions act on it, do you still end up with finite things? You think? Should be, right? Should be. But turns out it's not really that trivial. It's quite I reference all the proof for this section from a Japanese guy called Oda. He's really good at what he does, but his proofs can be very hard to understand. But I would like to show this proof mainly because this part right here, you can see here, relates to AG. We use the Hilbert basis. Yeah, so it's pretty nice. I think it'd be pretty neat to show you guys. Then the down there is I think it's some fancy trick lah. I'm not gonna go into it. Yeah. Oh, so, okay. Now we know that it's finitely generated, right? What generates them? We may assume that finitely many forms 1, F1 to Fr, these are polynomials of degree 0, D1, Dr, respectively generate the C algebra C, Z1, Zn, G. So now we define a polynomial map F that goes from Cn to Cr with the components which are our generators except for one, induces the surjection, this surjection thingy. Yeah, we go from CW1, WR to CZ1, Zn, G. And yeah, we let U be the kernel of this map, and we define V to be the set of X in all in CR such that H(x) goes to 0 for all H in U. That means like everything in the kernel goes to 0. Okay. Now our proposition, this one is just we define to be used in our proof lah. This proposition says, turns out that the image of F is V. Wow, interesting. It's a 0 set. Then Fz equals Fw if and only if Z equals G dot W for some G in G. This means that the two things would only end up in the same image if and only if they live in the same orbit. Yeah. F is like a polynomial map. You mean like, what does it do? I think it's like this. Just now that yeah. Can I continue? Yeah, so the proof also quite a bit difficult to read, but There are some things I would like to highlight, which is this part. Consider the ideal I equals if I equals the entire ring. Then there exists a polynomial P1 dot PR such that this equals 1. Does this remind you of anything? Yes, it's the Wigner standards. Very cute, very nice. Anyway, then we apply, we use we call, what's the size of a group? Sorry, I'm very blurred right now. Oh, we use the order argument. Basically, they assume, the idea is that we assume that, right, we assume that, God, I'm stuck. Skip. Different. Oh yeah, this is what we assume. We assume that I equals the entire ring. But yeah. And then since G is inside this invariant, then when we define the F, right, remember the surjectivity condition. So since this entire thing lives in the C, Z1, Zn superscript G, by surjectivity, there must be something living in C, W1 to WR such that this thing like this. Yeah. Then for some reason, Oda did some magic trick here. I don't even understand it myself. He do some sort of substitution, then he showed that actually if we assume that happens, then we get our order of the group is 0, which is very bad, a contradiction. So the second one, we want to show that, if things live in different orbits, they end up in different places. So, well, the first direction should be easy to show, right? And then now we show the second direction. Now suppose that Z not equals to GW, so they don't live in the same orbit, basically. So then there exists this C, Z1 to Zn such that the FC equals 0 and FGW equals 1 for all G and G. Because they don't live in the same orbit, so surely we don't get the same result. Yeah. Now we consider this entire sum thingy, which is G invariant, right? Because, yeah, F is G invariant. Now we do some trick. We lift G to H tilde. Then we find that, this one equals 0, this one equals 1. Because inside here, if we put the Z inside this multiplication, obviously it ends up to be 0, right? Yeah, then the same follows. And this shows separation, so they don't live in the same orbit. Great. Now, the above propositions show a one-to-one correspondence between the orbit space C and quotient G and V. Why is that so? Where did the one-to-one correspondence come from? I'm still thinking about it, but I think I have a rough idea. Basically, what we show here, right? It is a little bit like reminiscent of a bijective quote unquote, because you can see, right, everything in V or has something like everything in V comes from some orbit. You can see from here lah. And then this one sort of like giving one-to-one vibes. If I live in the one same orbit, I cannot have two images. So that's probably where it came from lah. Yeah. And this allows us to identify the quotient coordinate ring of C, and quotient G as C, Z1, Zn superscript G. And ta-da! We have an affine variety. Wow. Why? This like this coordinate ring gives me an affine variety. Yeah. So yeah, I'm correct. Okay. Now we define Kleinian singularity. Let G in SU2 be a binary polyhedral group. That, oh goodness. Okay, let's go fast. C square quotient G is an affine variety, and by the above. C square G is the orbit space given by spec. How surprising. Wow. And this X we equals to spec C Z1 Z2 superscript G is called the Kleinian singularity. So it's quite surprising, you know. To me, when I first read about this, I was like, Kleinian singularity should be a point, right? Actually, it's not. It's a variety. Yeah. And it's a variety where everything is nicer away from the origin, but when we go to the origin, everything collapses. I think it could be related to the, sorry? Black holes could be considered as a type of singularity. Yes. Yeah. I think in pure maths, we look at a lot of different types of singularities. Yeah, and this one is only a specific type lah. The Kleinian singularity. And then back to what I was saying, it seems that everything collapsed at the origin. Because if you think about it, the group action, right? The group action, everything in G, at the origin, everything fixes G, which is not nice. We don't want that. Yeah. That's one of the main ideas behind it. And then now the theorem, the algebra of invariance is generated by three variables x, y, z subject to one essential relation r x, y, z equals 0, where we define it in the following table. In other words, wow, the algebra of invariance coincides with the coordinate algebra of the curve defined by the this relation, i.e. they are like C Z1 Z2 superscript G is isomorphic to C XYZ quotient by R XYZ, the ideal lah. This is the table showing the relation. That's one important reason why we want to talk about Kleinian singularities. And this theorem in particular is because if we take X, which is our Kleinian singularity that we defined, which is the spec, right? And then just now we just prove it's okay, not prove that we showed we say that it's isomorphic. So I could say that it's equal to this thing over here, right? And we claim that this is isomorphic to VRXYZ. The last part is due to there being a canonical isomorphism of affine varieties. This one, actually, I'm not very sure. Okay. Intuitively, there should be some idea of why this may be true, because like spectrum is like set of prime ideals, right? And then, oh, maximal ideals lives inside it. So yeah, but the entire thing, I think it requires some scheme language, and I don't know. I didn't go into it. So yeah, and then VR has one singularity at the origin. We blow this up, then we should get our ADE diagram. This is the example. I can skip lah. Then something's missing. It's our next guess. Saya. If we, just now I mentioned if we resolve this resolve this singularity, I should obtain the thinking diagrams, which is like Joel's mention of how we did this using the algebraic geometry way lah. That's all. Thank you.
Page 22 is.
Yeah.
So I think I think your presentation is on the right track. I think everything is
Mm.
fine, but just that you don't have the details, right?
Yeah, unfortunately.
You have to fill it in.
Yeah,
Okay.
sure.
I don't think you can fill all of them in one report.
Mm-hmm.
Okay. Either I think you can speak to Adrian
Oh,
because those things are very important. Actually.
I think he's at the toilet.
I mean, he got choice,
Uh,
whether you want to do the E6 thing or help you fill all the.
yeah.
I don't think I can fix in like few pages.
Yeah.
Especially the spec equals to the
Yeah.
I1. Actually, it's quite important.
Mm,
Like what I said just now, it's actually not too hard actually. Like for example, spec of KT. What is spec of KT? Prime ideals in polynomial of one variable, polynomial ring of one variable. It's like all the maximal ideal. But we already know how to go from maximal ideal to points. Yes. That's how spec KT corresponds to a brief line, like K lines.
Interesting.
Most of, I mean, the easiest case is like maximal ideal is inside there. Yeah.
I actually got the reference. It's from the Igor's very old textbook. Yeah, he did. But yeah, he did.
Yeah. I think this line of logic is very good. But need to fill all the details.
Okay.
Yeah. I don't think can do it one report. So I think can be split.
Okay. Then actually, how about the theorem part? This one. The nice theorem.
Yeah, I think the nice theorem actually is not. I don't know. I would see from what I don't think it's very hard. Just that there's some line you don't know how to get through. I don't think it's super hard.
Because this one, I could not find.
This one.
Yeah, this one.
I thought you said the old ass group.
Oh.
I think the old ass group is doable.
Oh, that one's doable. I just need to fill in some gaps. Yeah. This one, I could not find a single more recent reference for it. It's all very old. A lot of old guys wrote it. Springer, Klein wrote it before Malaysia independence. Okay. Yeah, sure.
And you send to me.
Okay. Thank you. Anything else? No. One more? Table with the polynomial. This one? Yes. Oh, I got you. Actually, I think during my readings, I did encounter this question and I did consult TC about it. It's like, why the same thing or like two things?
He's asking about the end.
Oh, shoot. Where? I cannot see.
For the integral with the x power n plus 1, what is n minus 1?
Right. Let me check. And because I think we start from different like our 那个 subscript is different because normally we start from D4.
Oh, I see.
Yeah. So
how about the first one?
The first one, we did the -1 because I don't know why either, but there are lots of ways to write it. But if we write it like this, we like n to start from greater than 2 because it can't have A0. So yeah, and then D needs to be more than equal to 2 because D1, D2, D3 actually they're equal to A1, A2, A3, right? Yeah, so thank you, Syed.
Type A. Polynomial is
Oh.
Oh, that
Okay.
is the y square plus z square.
Yeah.
This one.
Yeah.
This one. I remember, right? There are ways to send, like, you could do a change of variables. I think that's how they do it lah. Yeah.
They did a change of. I think the first one is the same, but the one in whiteboard is SO3 and this one is SO2. Yeah, just for the yeah, but the difference between SO3 and SO2 is a change of variable. Yes. Yeah. Just a why is that? Why is that?
Okay. Anything else? Okay, thank you. Thank you, everyone.
Yeah, last.
话筒会正确放置。话筒会正确放置。话筒会正确放置。话筒会正确放置。
I such thing as blow up.
Loading.
Are you mentioning dynamics or explosions? Or
No.
you're just having a hair drying session?
Loading.
That's really mess.
I am Sunny Google. I want to go up AGE guiding. Then the first one is the AN cut one. The AN cut one, the polynomial is sy plus n and the power n plus 1 for all n. And it has a singularity at the origin. And it comes from the cosine singularity and the cyclic group. Then we want to resolve the singularity to obtain the AN guiding graph. So we do it in the projective coordinate T1, T2, T3, and we will couple up the our 3 tower and the B1, B2, B3 will T1 equal to 1, T2 equal to 1, and T3 equal to 1. So in the chart B1, T1 equal to 1, Y equal to ST2, and Z equal to ST3. We substitute that into the equation. Then we get this one thing and remove the common factor as well. We get the strict conform. And then for if we substitute T1 equal to 0 into the equation, it simplifies to the T square. So the electrical component must be the this one T1. I think it is the T1.
Your T1 is already fixed at 1.
Yeah.
That's why you think T1 doesn't know.
This still has a T1, but it's as
T3 or
T1 equal to 0 mean S equal to 0.
T3 or
I mean this substitute S equal to 0. 0 this is I want to get the extensional divisor. So I get the intersection and the extensional division is intersection this side is must be 0.
you get a point X into your Y, don't you think?
Then so the key square key 2 must be 0. Then we get the key 3 free. So the E1 is 0, 0, 0 times the 1, 0 key. And from the Jacobian of the gate transform, it says that for any X key 2, key 3 in D, it is moved. Then by symmetry of the xy coordinate, in B group we can get a state conform like this, and given the scalar derivation equal is different than the E1. So in B3, the T3 equals 0, we substitute it, then we obtain the an minus 2 singularity. And the extensional derivation given by the T1 T square equal to 0. So it has a two irreducible component corresponding to T2 equal to 0, and one is T1 equal to 0. This is just the same as the E1 and E2. And they are intersection and the 0.001. Then by the Oscar first roll up in the B3, the state conform is between the an minus 2, and if the singular point is the intersection point of the E1 and E2. If n equal to 2, the equation is moved, so we are done. If n larger than 3, so we must pull out the singularity and T1, T2, Z equal to 0. Then we go it in the alpha continuous T1, T2, Z, and the proposition coordinate R1, R2, R3. Then the E1 and E2 in this chart is become the T0, 0, and 0, T0. For the chart C1, we also obtain the C and the irreducible component E3. And E1 intersect E3 and 0, 0, 0 can 1, 0, 0. And for the chart C group, if it's similar, it intersection E2 and the 0, 0 and 0, 1, 0. And chart C3, we obtain the an minus 4 singularity. This also gives the two irreducible component E3 and E4, and E3 and E4 intersection at one point. So we know that E1 intersection E3 and E3 intersection E4 and E4 intersection with E2. Then for each blow up, we get the an index E4, and each blow out gives two essential derivation for n larger than 1. When n is even, we blow out the n over 2 times, we obtain the equation will become small, so we are done. When n is odd, we blow out it at the scale of the n over 2 times, we obtain an A1 type singularity. For now, we want to solve the A1 singularity. By the previous blow up or not, we obtain the x1 plus 2 z squared equal to 0, and 2 extensor derivation is equal. Then in the third T3, the state conform will become T1, T2 plus 1. So for z equal to 0, the T1, T2 must be -1. This is just this only one extensional divisor. If the E3 equal to 0, 0 and A is negative and A. And E1 and E2 cannot be seen in the chart. And so for T1 equal to 0, the chart, we can find the state conform R square, R2 plus R3 square. So the explanation direction is this, and this is same as the E3. And so we can find that E1 intersect E3 at the 0, 0 and 1, 0, 0. By symmetry, the B1, we can see E2 and E3 intersection at one point. Then if n is odd, by blowing out the field of the n over time, we can solve the singularity and give an irreducible component of the extensional derivation. So the goal graph is this. Now we come to the GN card. It's defined by the surface x squared plus y squared z plus z power n minus 1 for all n larger than 4, and it still has a singularity at the origin. And it comes from the binomial Algebraic group. So in chart B1, K1 equals to 0. We substitute K, we get the straight transform x squared plus y squared plus z. The second form, if we substitute x equal to 0, it simplifies, we get the 1 equal to 0. So the external derivation does not intersect in the chart B1. In B2, we obtain the straight transform negative. Then when we substitute y equal to 0 into z, it's the case. So P1 must be 0. Then the extensional derivation is the 0, 1 key. And this equation has a singular point as 0, 0 and 0, 1, 0. This is just a A1 type singularity. So we need to bold out it again. So we put it in the key 1, y key 3 coordinate. And we can obtain the essential derivation like the gamma 1 by 1 negative a square and a. And the equation is moved. In C2, we also obtain a linear one. And this is the extensional derivation is same as the gamma 1. So, and get in E1 and gamma 1 intersection at the 0, 1, 0. And this so the Jacobian, the equation is moved. For the C3, it is linear to C2. Then in B3, this the state conform is between the item is T1 square plus z T2 square plus z power n minus 3. So it has a singular point and the 0, 0, 0. The isolated derivation is given by the 0, A1. It is just a Dn minus 2 type singularity. When n equal to 6, it has a singular point. So we brought out it again. Then we get the E1 in this chart is become the 0 key 0. Then for chart C1, the straight transform is more. From chart C2, it is linear to C1. We also obtain a standard derivation negative square and it intersection under 0, 1, 0. And for C3, the straight transform is the Gn minus 4. And the external derivation is the 0, A1, and it intersect with the gamma square. And then this is both are regards the time from Gn. For n larger than 5, its both of one time is given to exponential derivation. When n is even, we brought out the n over square minus square time. We will get the default type. When n is odd, we brought out the scale of the n over square minus 2 times. We get a defined type singularity. Now we discuss the case for the default singularity. In this way, we obtain an exponential derivation, the gamma 1. In B3, the third transform will become the T1 square, T2 square z plus z equal to 0. And it has a good singular point and the 0 plus positive, negative I and 0. So we need to pull out in this group. The extensional divisor is this. So we also optionality, we just go out on the 0, negative 1, I 0. Then with that, v equal to k square plus I. The equation will change to the k 1 square plus v 2 square z minus 2 I v z equal to 0. and we group it in the coordinate T1 VZ and EC1, we get the strict conform, so it is moved. And the alternate divisor is the equal 0, 0. E3 is so this is the CS1 square. And give this a extensional divisor. We can find the E1 intercept E2 and the 0, 0, 1. So similarly for 0, 1, 0, we obtain the E3 and E3 intersection E1 at one point. Then we done the case for the E5. Then now to the B5, when n equal to 5.
I think it's the same thing, right?
It's not same because the D5 is give a D3 and give it the A3 card. The D5 you ball out each time it become the D3. It is the A3 time. D5 ball out one card but take D3. So it is the A3. And thus it is the
I think it's the same.
same as A3 and the intersection and one time add.
But I'm curious, why no picture here?
Because I
Where's the ADD thinking diagram?
ADE thinking
You
like
only tell us for intersection, for intersection, for intersection. We don't know where intersection.
I cannot draw it lah. I can't recall. 现在两个点就可以了。
Cannot imagine the intersection.
Why need to imagine?
Huh?
Why need to imagine?
Why need to imagine? I thought Lydia said you need to link to the thinking diagram. I didn't see any thinking diagram.
But I already saw it has intersection in one point.
Yeah.
So it is the change to the goal graph of this. The goal graph of the intersection of the exponential direction.
What you say?
You can from the intersection we can see.
Yeah, show it. I know, show it.
But I either compute already. Why need to go?
Why need to draw? Okay. So this is a presentation skill. If you don't draw, people will get lost easily. Or people won't listen to you. You also don't like teacher presenting bad, right?
I don't care.
Right. you like teacher presenting bad. Don't like, right? You have to draw. All these calculation is not just algebra, right? Not just those, right?
But algebra is enough.
Enough. But I mean, like for those who cannot get it, then cannot get it. Yeah. So the point here is to like make more people to understand, right? You understand? Yeah. I mean, like, in other words, actually, calculation is not enough from my point of view, because all these calculations represent geometry, right? This course is not algebra, it's algebraic geometry. So we did not see geometry here. We only see algebra. Calculation is not hard, but where is the geometry? You understand? Right. I thought just now your group mate throw you a job to draw the ADE thinking diagram. Do you have the diagram?
But it is in the is it? You want what? What thing?
I didn't know how all these singularities can became like blow ups. Like it's it like it. I don't know what's the blow up. I don't know what is the blow up from your perspective. I don't even understand how singularity, how all this singular, how many five singularity actually can be blown up. I also got confused.
要请有个 singularity point to a projective line. And yes, yeah.
Yeah, I think your question is very good, but he already assumed that you know because we did. So from the point of presentation, actually what she asked is very important. You have to like go through whatever you want to use. Not in big details, at least like remind people what it is. Correct or not? Correct or not? Some teacher just assume you know, right?
Yeah.
No need to explain to you obvious. You like that kind of teacher?
Okay.
Then don't be that kind of teacher. So at least recall for them how to check our singularity, and then tell people what the process will go out. If no, people no need to follow your side already, you can leave the room already. Don't come to your class. Correct or not?
给了给了 this kind of.
啊？Correct or not？
你不会帮他就不给 no.
什么？不给 not 啊？See, teacher punish you. See? So I mean, like, don't be that kind of person. So you need to start from whatever you want to use. Tell people what is it. Even if you don't want to go deep into it, at least you need to mention it. Otherwise, then people just get lost. Then don't want to enter class. That's the story.
Yeah, basically.
Right. Okay. So last thing. So tell us how to link the linking diagram picture to this calculation.
For the A and you have to. Can you get the E1 and E2? And the intersection point is still a singularity.
Yes, show with the slide. Can you do this calculation?
This one. Then you get the E1 and E2. And the intersection point is still a singular point. Then we want to pull out it again, so we change it to a new coordinate. And it is then you go up it again, you will give E1 and you go up it, you will give go E and E4. And the intersection point is still another. You go up on camera, give you a and you go on the X of the flag data. It's you take the assembly divisor to a form factor and it get its intersection You just get let's connect with Google. Like this.
Any question?
Okay, can we invite the last group member all here? So this is what happened if your maths teacher teach calculation. Boring, eh? So you seldom see calculation in the pure maths class. But I mean, basically, it's just repeating to do the blow up. Can you recognize or not? For those who know blow up, if you don't know, then you won't know it. But for those who know blow up, right? Okay. Any other question for them? You got a question, yeah.跟他讲要完了。Yeah, because we got a booking until 6. Hey, got. 5 more minutes, we will leave. Okay, thank you. Okay, continue.
Of why is it that the diagrams you write don't have multiple edges? You don't get the diagrams of type B, of type C, type G, type F. You only get ADE. So why do these multiple edges not occur?
The multiplication is the computation is basically using character theory, but I didn't go into detail what the computation just now. But you can just do the computation and you find the dimensionality is actually just one. It cannot be other. Yeah. So it's one from.
So you're saying that from the character side,
Yes.
the fact that there's only one edge means that all of these reducible representations appear only multiplicity at most one.
Yes.
So what does this mean on the blow-up side? Only one edge.
Oh, the block side is basically you look at the exceptional devices and then you look at the irreducible components, and then you see that actually they just intersect two reducible components, intersect one point, and then if you draw it pictorially, you circles, and then it just resembles the Lie diagram.
So one edge means that it's only at one point.
Yes, it's just at one point.
I see. Okay, thank you.
Okay, any more? Okay, if not, we will dance McKay groups again. So congratulations to everyone for finishing their seminar. So we come all the way from a reading seminar to a proper seminar. We do really hope that in future we have a proper research group on this thing. So hope that we can attract more talent to work in this field in future. Okay. So shall we go for dinner? Yeah, we got a guest here actually. Do you want to introduce yourself? Yeah. Do you want to introduce yourself? Anything you? How old are you actually? 24, so it's 2021. 2020. Sorry, 2001. 2001. Okay.
Technology mainly. Kisa invited me because all of you seem to be very passionate, very excited to do math. The kind of math you do here seems to be very good standard, I say.
Okay, thank you. Yeah. So if you like, we can go dinner together with him. Should we go McDonald's or Mama? Huh? You go Mama or McDonald's? You go back, okay. Yeah. Hey, 帮你们拍照，一定帮你们拍照。But we need to decide first and then we can pack first. McDonald's? McDonald's better? Is there a vegetarian Starbucks? I'm not sure. Huh? You are vegetarian. Okay. McDonald's Mama McDonald's 没有。好吧 Mama 有 Mama okay. Okay, then we go to the Monet Mama. Okay. For those who want to go dinner, we can go together. To Monet Mama. Okay, 来，找一个照。所以跟他们一起。我们一起还是我们一起？我们一起，可以啊。OK，可以。
我排这个。